Welcome. We have discussed about the orbit, space segment, the link budget, the propagation effect, ground segment, and then we talked about a network system in that multiple access, different types of multiple access. Now, we will try to talk about certain issues we face in this type of communication, which is wireless and which is a long delay and which has a probability of error is quite high. Now, let us see the first part, that is, it is a long distance repeater. The satellites are quite high in the sky. So, the power that is required from satellite to ground to receive properly with good sensitivity, you need to transmit large power from satellite, and similarly from the ground to satellite. So, once we try to transmit larger power, we have to look at the power amplifier and take the maximum power out of it. Now, from any device, when we try to take maximum out of it, it goes into nonlinearity. So, as we know that any amplifier at a very low input level, there is noise. Even if you do not give any input, there will be certain thermal noise. So, there is nonlinearity at the very low level. Similarly, when you go to a higher level up, there will be again certain distortion that is limiting by the power supply supplied to that amplifier. Now, it is not only amplifier, there are many devices which generates and shows nonlinearity. In fact, almost all practical devices, active devices, they show nonlinearity and nonlinear characteristics. So, we will see how this nonlinearity can affect our communication system. So, our topic is nonlinearity, and what we cover is and this topic is what we will cover the nonlinear devices, certain terms we use, used. Those terms define what type of nonlinearity it is, and then we will talk about nonlinearity, not only single device, when they cascaded, nonlinearity in cascaded system, when they put one after another. And of course, we will see the effect of nonlinearity, and very briefly we will touch upon the mitigation technique. This is a general form, there will be mix of this while we discussed. So, let us take a nonlinear device, and let us say the device is nonlinear, and it has the input. Let us say we give a voltage input V I, and it goes to the output and it gives a voltage V O. Now, in general, a generalized form of nonlinear expression, that V output can be modeled as a Taylor series. So, it can be written this way, simply A 0 is a coefficient, then A 1 V I, then A 2 V I square, then A 3 V I cube. Like that we can continue, and depending on the coefficient values, that nonlinearity can be generated. So, this is a very general term. So, out of that we can define that this is a DC term if we give AC input, and this is a linear term and this is a linear output. This could be this is a squared output, like that. Now, if we say that all other coefficients are 0 and only A0 is only non-zero coefficient, then the device is a rectifier. Similarly, if A1 is only non-zero coefficient, then the device, if A1 is less than 1, then output will be less than the input. So, it is attenuator, and if A1 is greater than 1, then it is amplifier. This is how it is expressed. Similarly, if A2 is the only non-zero coefficient, it is generating higher and higher frequency. It is frequency converter. So, that is how based on the Taylor series model we can define, based on different coefficient, what type of system it is. But in practice these things occur together. So, several of the coefficient may be non-zero in practice, but this is a ideal modeling situation. Let us see. Let us try to give a input. Let us say Vi is V cos omega 0 t. Give one frequency and a voltage for that. So, this is the input. Now, how V0 will be written? V0 will have a DC component, that is A0, then we will have the linear component omega 0 t, then we will have a square component, then it will have a cube component, like that. Now, if we take this cosine square, cosine cube, this term, and use certain trigonometric identity and separate out that single frequency component and DC component and higher other frequency component, we can group them like this, that A0 plus A2 V square by 2, that will be our DC component. Then A1 V plus 3/4 A3 V cube cos omega 0 t, that is the fundamental component, but this with this coefficient it will go. Then A2 V square by 2 cos 2 omega 0 t, that is double frequency component, will have this type of coefficient. Then A3 V cube by 4 cos 3 omega 0 t, the another higher order component of frequency with a different coefficient. So, in these let us assume that this is the amplifier. So, we will take the fundamental component, and what is the amplifier gain? The gain is B0 by Bi. So, this coefficient, that is A1V plus 3/4 A3 V cube by V, and then that comes out to be A1 plus 3/4 A3 V square. Now, here A1 and A3 is that generally practically this A3 is many times opposite sign of A1. So, in that case it will grow linearly, but after some time it will deviate from linearity. It will look like briefly it will go straight and then deviate from linearity. This is V and this is V out, V in I can call. So, that capital V as we increase. So, this is actually what is happening, it is gain compression. I can call it a gain also. This is gain I can plot. Gain, if I plot, then gain will go linearly and then it will try to deviate from linearity. So, it is called gain compression. So, this is one of the major effect of nonlinearity, that gain will go linearly and after some time it will saturate. Let us see what happens if we put if we try to draw this characteristics in power. What happens in power? Say let us call this one as P I in dB, dBm let us call, and then this is P out in dBm. Now, once it is plotted in terms of power, it is linear slope and then it deviates from linearity. So, when it deviates from linearity, this could have been the linear situation, and when it is 1 dB down from here to here, let us call this is 1 dB down. This point is defined by the device suppliers or manufacturers, that at this point we start getting the nonlinearity or it is getting into saturation. So, this point from the input side, it is defined as input power of 1 dB compression point. Similarly, this is called output power 1 dB compression point, 1 dB getting compressed. So, therefore, it is away from linearity, it is compressed and it is going away in the nonlinear direction. Now, this gain of this amplifier, of course, power gain is a ratio of P out by P in, and this slope when we do it in dB, it is 1, that is it is a linear response, and when the P out starts deviating from the linear response, we get into saturation, and when it is away from the 1 dB of linearity, it is called 1 dB compression. Now, this is defined in terms of either input 1 dB compression point or output 1 dB compression point. If it is referred to input, it is called input 1 dB compression point IP 1 dB, or output 1 dB compression point, which is OP 1 dB I have written here. Generally, that in practice the higher one of this is specified. In case of amplifier, output 1 dB compression point is higher than input compression point, because the gain is multiplied to that. And let us say a lossy device called mixer, which is a nonlinear, where the input 1 dB compression point is higher. So, in case of mixer, input 1 dB compression point is referred. So, when simply 1 dB compression point is said, then we have to check whether it is referred to input or it is referred to output. But generally we will be talking about amplifier. Of course, sometimes we will come to mixer, we will always refer it. We can say 1 dB compression point as OP 1 dB or IP 1 dB compression point. Now, let us see that what happens with a single carrier input to a nonlinear device. That is, single carrier means single frequency. So, it generates, we have seen that it generates a DC component, it generates a fundamental frequency which is omega 0, it generates a multiple of frequency which is 2 omega 0 or 3 omega 0, like that. So, these characteristics of multiple frequency, multiple of the fundamental frequency is used in frequency multiplier. Like this, we have at satellite we get input in 6 gigahertz, let us say, uplink which has gone to the satellite, and after LNA it has come to a down converter which is nothing but a mixer and then a local oscillator, and that local oscillator contains a crystal oscillator which is generally, this is crystal oscillator which is generally of the order of 100 megahertz, and to get output of 4 gigahertz which should be the downlink after this down conversion, I need to give 2 gigahertz here. So, this 100 megahertz has to be multiplied and brought to 2 gigahertz. So, this frequency multiplier is n equal to, in this case, 20. So, you get a 2 gigahertz. So, this is one of the place where this nonlinearity is used. It is used in mixer also, that for a single frequency, when it is going up through a nonlinear device, we get this multiple of the input frequency which is n times of input frequency, and there may be, I mean here it is simplified and shown, it in one stage it may not be taken as 20, it may be multiple stages and in between amplifier may come, but this is the concept of the frequency multiplier. Now, let us go into the amplifier. In amplifier, generally in satellite communication we have seen last period multiple access, multiple carriers are coming. So, let us take a simplified case of 2 carrier input. So, 2 carrier input is, let us say, V I in that case, and both the carriers have same amplitude. So, V cos omega 1 t and cos omega 2 t, both have the same amplitude V. This is for simplified calculation. In actual case, it may be, most of the time it will be V 1 cos omega 1 t or and V 2 cos omega 2 t. Each amplitude may be different depending on the input what is being supplied by different carriers. So, the V output will be in that case by Taylor series, if we go A 0 A 1 V cos omega 1 t plus cos omega 2 t, then A 2 V square cos omega 1 t plus cos omega 2 t whole square, then A 3 P cube cos omega 1 t plus cos omega 2 t cube, like that it will continue. Now, if you simplify these square terms and cube terms and then use certain trigonometric identity, then you will find that in addition to the fundamental components omega 1 and omega 2, you are getting the higher order components like 2 omega 1, 3 omega 1, like 2 omega 2, 3 omega 2, and also you will get omega 1 plus omega 2, omega 2 minus omega 1 or 2 omega 1. So, like that there will be lot of other frequencies which are generated other than fundamentals. All those frequencies are called intermodulation product. Now, let us try to do it mathematically. Let me show you. That is that output spectrum of omega 1 and omega 2 will be in the form of m omega 1 plus n omega 2, where m and n could be 0, plus minus 1, plus minus 2, plus minus 3, like that. This combination of two frequencies are called, either you can call it spurious, in this case we will call them intermodulation. This term I have used earlier, but we have not defined. It is intermodulation product. So, let us say m is equal to 2 and n is equal to 0, then what you will get? 2 omega 1, which is second harmonic. Of omega 1. So, we can say there is a order of m and n. So, the order is defined order of intermod product, we can define as mod of m and plus mod of n. So, we can see the second order components are 2 omega 1, 2 omega 2, omega 2 minus omega 1, then omega 1 plus omega 2, like that, many terms. Now, when this omega 1 and omega 2, when they are closely spaced, then the multiplication or addition subtraction terms will be far away from the fundamental frequency omega 1 and omega 2. Now, similarly, we can see in the cube term, has 6 third order intermod, that is 3 omega 1, 3 omega 2, 2 omega 1 plus omega 2, omega 1 plus 2 omega 2, 2 omega 1 minus omega 2, 2 omega 2 minus omega 1. Now, these first four, 3 omega 1, 3 omega 2, 2 omega 1 plus omega 2, omega 1 plus 2 omega 2, you can look at from this, you can make out they will be far away from the fundamental. Or omega 2. But these two products, 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, if omega 1 and omega 2 are closer, their difference also becomes closer. So, they will be coming very near and they may fall within the transponder, and with modulation, if it is pure carrier, then they will be away by omega 1 minus omega 2 delta omega. But if they have modulation, then some of these frequencies will fall within the filter bandwidth of omega 1 and omega 2. Let us try to draw a simplified diagram. Let us say this is the frequency, and here somewhere I have closed them together. This is omega 1 and omega 2. So, omega 2 minus omega 1 will be here, very near to DC. but 2 omega 1 minus omega 2 will be coming very near. Similarly, 2 omega 2 minus omega 1. Then you will find far away that omega 1 plus omega 2 and 2 omega 1 and 2 omega 2, these terms. So, these first 4 terms will be far away, whereas these terms 2 omega 1 minus omega 2, 2 omega 2 minus omega 1, which are third order intermode product, will fall very near, and if there is a modulation here, the bandwidth will be more, and modulation here, the bandwidth is more, then the multiplication of this frequency to this frequency will fall within the band. Now, since the time is short, we will continue the discussion in the next period. Thank you for the time being.